Speaking of that hardware infrastructure, take a look at this article from Air Street Press. Notice the headline there? The AI Factory Illusion. We really need to kick off this explainer by looking at a very specific and honestly highly political industry rebrand. Recently, leading figures, think NVIDIA's Jensen Huang and OpenAI's Sam Altman, basically stopped using the term data centers, just dropped it. Instead, they've started calling the backbone of AI infrastructure AI factories. Now, as the report points out, we need to look at this totally neutrally. This isn't just some casual swap of words from a marketing department. It's a highly strategic move where raw computational power and geopolitical policy are essentially colliding.
So, here is our roadmap for today's explainer. 1. The AI factory rebrand. 2. Simulating persistent worlds. 3. Agents evolving themselves. 4. AI in the physical world. And 5. The future of planning.
All right, let's jump right into Section 1, the AI factory rebrand.
So, why do the words we use actually matter here? Well, according to the analysis in the report, retiring the term data centers in favor of AI factories is a really subtle but politically astute linguistic shift. By leaning into Trump-era terminology that's hyper-focused on reshoring American manufacturing, the AI industry is intentionally repositioning itself. They no longer want to be framed as these abstract, cloud-based software entities. Instead, they are deliberately aligning with nationalist industrial policy, presenting their massive server farms as vital, physical manufacturing hubs. It's essentially about securing political goodwill and leverage by framing data processing as a tangible, hard industrial asset.
Okay, moving on to Section 2, simulating persistent worlds. And this timeline right here brilliantly illustrates the sheer mind-bending speed of development we're seeing. Just look at Google's Genie model. In a span of just 18 months, we went from February 2024, where Genie could only generate these low-resolution 360p interactive worlds from a single image prompt, to December, where Genie 2 added persistence and memory. That meant actual object permanence over several minutes. But now, fast forward to August 2025, and Genie 3 gives us fully dynamic, user-steerable 3D environments. What's absolutely incredible here is how this allows developers to generate complex game environments, create rich animation, and seamlessly make many motion and animation motion to add a character with absolute full control to interact with that space. It's no longer just making a flat picture. We are literally building a dynamic 3D training substrate for agents and sim-to-real robotics.
And OpenAI is pushing a very similar boundary over with Sora 2. It's inching closer and closer to being a true, persistent world simulator. Sora 2 now includes synchronized dialogue and sound, vastly stronger physics, and much tighter multi-shot control. But tying right back to that incredible ability to make many motion and animation motion to add a character, Sora 2 can now actually insert a short cameo of a real person, perfectly matching their voice and appearance directly into the generated footage. The animation and motion capabilities are just becoming hyper-realistic, allowing for entirely consistent character rendering across all these varying simulated environments.
Now, what actually happens when you put an AI agent inside one of these simulated worlds? Well, look at the offline diamond challenge data over on the right. Reaching a diamond in Minecraft is a notoriously complex, super long horizon task for an AI. Those blue bars on the far right, that's Dreamer 4. It significantly outperforms the baseline models, and that includes OpenAI's VPT. And here is the absolute kicker. Dreamer 4 achieved this using offline data only. Oh, and it did it using roughly 100 times less labeled data than the OpenAI model. Literally 100 times less.
So, how exactly did Dreamer 4 pull that off with such crazy efficiency? It all comes down to a new concept called shortcut forcing. To put it super simply, standard models often kind of cheat by looking at the final outcome and correlating it backward. It's exactly like guessing how a magic trick works, only after you've seen the big reveal. Shortcut forcing explicitly contrasts predictions with and without the true actions. It literally forces the world model to depend on the actual actions being taken to predict the next frame, rather than just lazily relying on hindsight correlations. And because of this massive leap in efficiency, Dreamer 4 can run its complex video world model at interactive, real-time frame rates on just a single GPU.
Which brings us to Section 3, agents evolving themselves. I really want you to read the definition here carefully. The Darwin-Gödel machine. I know, it sounds like pure science fiction, but I assure you it is a very real current milestone. We are talking about an AI agent that is trapped in a continuous, self-directed evolutionary loop. It actively rewrites its own underlying code, tests those specific changes empirically on coding benchmarks, and if, and literally only if, the new variant performs better, it archives it as the brand new baseline. Let's actually trace the flow of this self-improvement loop starting from the left. First, we have the archive. The parent coding agent selects itself and spawns a child agent by modifying its own code repository to try and solve a task or improve a feature. It then ruthlessly evaluates that child on a strict benchmark. If the child's code gets a higher score, well, that child is added to the archive and becomes the new parent. This loop is producing steady, totally measurable generation over generation gains on benchmarks, all without human engineers manually tweaking the system whatsoever.
And the crazy part? The Darwin-Gödel machine isn't some isolated case. It's part of a massive, industry-wide trend of AI generating its own training grounds. For instance, with Omni-Epic, foundation models are literally generating the code for both the environment and the reward systems, filtering for tasks that are actually useful to learn. Meanwhile, systems like Kinetics are out there training general controllers in massive, procedurally generated task spaces that eventually transfer over to human design levels. The AI is essentially building the gym, inventing the workout routine, and then training itself.
Let's take that straight into Section 4, AI in the physical world.
Now, when it comes to actually putting these advanced AI brains into physical robot bodies, the industry is currently split right down the middle between two competing training philosophies. On one side, you have insulation. This involves taking a massive vision language model, freezing it so its core weights can't change, and only fine-tuning small, specialized action expert heads on top of it. This prevents the model from forgetting its broad, general knowledge when you only have a tiny amount of actual robot training data. But on the other side is the end-to-end approach. This means unfreezing the whole model and training the entire network directly on the task data. It's definitely riskier, but when data is abundant, it allows the network to deeply internalize things like physics, contact dynamics, and complex scene geometry. You can really see this if you look at the Pi 0.5 diagram on the left. That large central block is the vision language model backbone, and it's totally isolated. Only that small, yellow action expert block on the right is actively learning the continuous physical actions. That's your insulation approach. Now, contrast that with the small VLA datagram on the right, which represents the end-to-end approach. It integrates everything from community datasets directly through the attention layers to output physical actions. The report explicitly notes that if robotics data ever reaches the massive scale of text data, this end-to-end approach of models like small VLA will absolutely dominate the space.
And finally, Section 5, the future of planning. Ultimately, the key to safety in robotics is forcing the AI to basically think out loud before it physically moves. And we're seeing this exact approach pop up across the industry right now. MIT is introducing explicit plan tokens, requiring the LLM to output its reasoning before giving a final answer, which gives human auditors something to actually inspect. Over at AI2, Molmo Act takes this a step further for robotics. Before issuing a motor command to an arm, it emits visual artifacts, like drawing a depth or trajectory sketch right on the image, so you can see exactly how it plans to manipulate an object. And Google DeepMind's Gemini Robotics 1.5 uses a very similar architecture, separating a high-level reasoning planner from the low-level policy that actually executes the physical movement. The whole goal here is just making complex debugging possible for us humans. Which brings us to our final thought for this explainer. We started all the way back at the infrastructure, the AI factories. We watched as AI learned to simulate its own dynamic physical worlds, complete with mind-blowing character animations and motion. We saw it rewrite its own code to literally evolve, and finally, we saw it step off the screen into the physical realm to pilot real-world robots. So, as these systems become increasingly autonomous from top to bottom, I want to leave you with this question. What role will humans actually play in the AI factories of tomorrow? Thank you so much for joining me for this explainer. Keep learning, and I'll see you in the next one.